Right then, now we've got a few more people in the webinar, I think we should just get started. Welcome back to the All Things Hydrogen webinar series. Today we have Victoria kicking us off with the development of a novel solid oxide tubular electrolysis cell for hydrogen production. And if you have any questions, just leave them in the chat and then we'll get to them at the end. So over to you, Victoria.
Right, okay, I'm going to introduce myself and then Ajit. So I'm currently working with the design of the novel solid oxide electrolysis cell, and previously I worked in the Newcastle University with the flow-induced vibrations for multi-phase flows, and previously I did vortex-induced vibrations of subsea pipelines. Ajit?
Yeah, I'm Ajit. I'm working with Victoria, and we are working on the novel solid oxide tubular electrolysis cells for hydrogen production. And before I did my PhD in the area of solid oxide fuel cell materials, we produce a planar solid oxide fuel cells. Now we are developing the tubular electrolysis cell for hydrogen production. We are collaboratively working with the Robert Gordon University, and of course, a part of it's funded by the UKRI research call, of course. Thank you.
Right. So overall, the project that we're working on is Metasis. It's about scalable metamaterial thermally sprayed catalyst coatings for nuclear reactor high temperature solid oxide steam electrolysis. And the project pursues the goal of developing a new high temperature steam cell of a tubular configuration for the purpose of hydrogen production, which could be used at a different scale. And this is a joint project. So at RGO, we perform modeling and design optimization, which partially aims to assist the experimental program. And Vinod Rajendran, here he's a research assistant helping us, and he's in charge of the low temperature testing to characterize materials. And all high temperature testing is performed at the University of Surrey by Ajit, and he will tell about this in the second part of this talk. I will start with some general introduction and with the knowledge that we all have in common. So hydrogen is a gas without smell, color, or taste, and it can be stored in a gaseous condition at the ambient temperature or in a cryogenic condition to suppress its volume. And the relatively high volume of hydrogen per unit of energy when the gas is stored is one of the challenges when it comes to end consumers. However, already now, hydrogen is successfully used for refining petroleum and producing new materials. And as a way of energy storage, it can be easily converted into electricity and used for any devices from a small to a large scale. And currently, hydrogen is used to power vehicles on our roads. If speaking about electrolysis cells, not only hydrogen can be obtained from this process successfully, you could also make use of oxygen, and potentially you could treat it even as a primary product. And one of the most interesting applications is the solid oxide high temperature electrolysis for the purpose of obtaining oxygen in the area of space exploration, where generated oxygen can be a part of a new breathable air. Another use of electrolysis or co-electrolysis is process when we have excessive carbon dioxide as a feedstock material, and we can convert it into some useful products. If we're diving into the specifics of the solid oxide electrolysis, it's in general a combination of the reduction and oxidation reactions happening at high temperature. And the process starts with the incoming flow of the high temperature steam, which gets split into the charged particles of hydrogen and oxygen in the porous cathode layer. Positively charged cations of hydrogen are accumulated around the negatively charged cathode layer. They gain electrons in the reduction reaction, and the flow out of the cell has an increased proportion of hydrogen and the remainder of the high temperature steam. And in the meantime, oxygen anions, they pass through the membrane, and at the anode side, the negatively charged anions give away electrons and form oxygen molecules, which exit the appropriate fluid channel. And some inert gases may be used for fluid channels to be a component of this flow, such as argon gases in practical applications. Overall, water as a feedstock substance stands out with its relative availability and environmental friendliness, and the water electrolysis technologies generally differ in the type and charge of particles which are transferred through the membrane and respective directions of particles traveling. So for solid oxide electrolysis, it would be oxygen traveling towards the anode, in the alkaline cells, it will be traveling towards the cathode side, and in the PEM, it will be traveling towards the anode side. So water electrolysis technologies are also different in the temperature range and in the type of the materials used for all the functional layers. And as comes from the name of it, solid oxide technology stands out for the use of the solid materials for all functional layers. However, at present, dominant electrolysis cells are proton exchange membrane cells, shown on the slide, and the alkaline electrolysis cells. And they are successfully commercialized. Solid oxide technology is not yet fully commercialized. It's not a mature technology. And this slide, the current slide, presents some quantification for comparison of these three technologies. One of the differences is the temperature ranges. So alkaline and PEM cells operate closer to the ambient temperature, and the solid oxide is oriented toward the high temperature range, up to the 1000 Celsius. The solid oxide electrolysis cells have production rates at approximately the PEM cells, at least according to the data from 2017, and increasing stock lifetime for the solid oxide electrolysis and reducing capital costs are still open research questions which could help commercialize this technology. Also, you could notice that for solid oxide electrolysis, you would have a reduced cell voltage and a wide range of the current densities. So this results in a wide range of electric efficiency characteristics for the solid oxide electrolysis. And here the current voltage curve is one of the main characteristics for the electrolysis process. So while keeping the cell voltage as low as possible, we could have the current density climbing. And this is one of the main goals when we are improving the design of the solid oxide electrolysis cells. However, the current density is bound to increase with this high consumption of the power grid. And the graph on the right illustrates the dependence that for each functional layer, it is possible to reduce the consumed voltage with the elevated temperature. It comes from already early research in 2007. And this, what you can see from this figure is that this reduction of the needed voltage is going to be different for each part of the cell. And this is also one of the opened research questions. What is the best temperature range for which configuration and which combination of materials? Overall, if we are to list advantages of the solid oxide electrolysis, it comes to the high efficiency, which could be achieved by the combined use of the electric and the thermal energy. So this efficiency is achieved specifically in the high temperature conditions. Also, this combined use of energies makes this technology compatible with a wide range of systems where you can have either excess thermal energy or excess electricity or excess of both. And what is good about solid oxide cells is that they're well suited for the intermittent operation, and it goes for electrolysis cells, fuel cells, and reversible cells. So however, how exactly you're going to use materials for those cells is going to be different depending on the application, so that your design that you make for an electrolysis cells would be different from the best fuel cell, and they both will be different from the best reversible cell. And also use of solid materials for all functional layers, it significantly simplifies how you're going to transport the cell, install the cell, and how it's going to work, because you don't need additional circuits for the fluids for functional layers. So, and another thing is that solid oxide electrolysis operation is environmentally friendly. So this could be counted as 5 main advantages of this technology. And concerns which partially come from the table that I've shown, the data of comparison for 3 types of cells, is that, first of all, for now, it's quite a costly technology. So it needs some innovation, especially in material side. High temperature conditions, they lead to the significant material degradation, and also some parts of the fabrication of the cell or how they're going to be recycled in the future. It's for now open research questions, and majority of innovations right now, they touch design of the actual cell, and there is some lack of innovations related to how to commercialize this technology and how to manufacture them in different quantities for specific designs. Just by the number of the current research, combined use of energies leads to integration possibilities with some specific systems, because a high temperature cannot be generated by many systems, but there are some specific ones, like a wide range of nuclear reactors that operate at high temperatures above 600 degrees. They're very suitable for integration because in the system there is excess thermal energy, and other systems with which you could use solid oxide electrolysis are solar plants, wind farms, hybrid energy systems. Potentially could integrate it with aviation and some spacecraft systems where high temperature residuals may occur. So if you are considering integration in terms of the thermal energy, so you would have some normal consumers, for instance, but demand normally fluctuates with some pattern, often cyclic pattern. So when you have the troughs in the consumption of the electricity, you would potentially give this power away to the high temperature electrolysis stacks, and you could run these cells intermittently in order to produce hydrogen. But there are a lot of open engineering questions when it comes to the integration with the specific system. So when you are developing a solid oxide electrolysis cell, there are several design decisions that have to be taken at the very beginning when you're developing this type of design. And one of the principal questions is that how you're going to ensure the mechanical support for the cell. And defining question here is that which layer is going to be the thickest. And the main trade-offs that you are making here is that your thickest layer should ensure the optimal mechanical stability, but there will be definite losses when your fluids when your charged particles are going to pass through this layer, because they are going to lose this electric or thermal energy on the way. And for the current project, we are working with metal-supported cells. And this allows to ensure the highest mechanical stability, especially counting that we are going to develop the cell in the university lab. So the safety concerns are going to be one of the main ones when arranging high temperature testing. This is why we're working with the metal supported cells. For other support types, this trade-off is similar. The layer which is going to be the thickest is a cathode or dense electrolyte or a thick anode. Sometimes they would not allow sufficient mechanical stability, as comes often with anode supported cell designs, but some of these supports may allow operating for solid oxide cells in a lower temperature range, such as anode supported design. So this is one of the design decisions that have to be taken early. Another type of a design decision is about whether you are designing a tubular or a planar cell. And there are already some designs developed by companies, and they are very, very different in terms of geometrical configuration. One of the things that can be different is just the basic geometry of the gas channels, that if you have a tubular cell, you may choose between a single internal gas channel and what kind of shape your external channel is going to have. And potentially you could use, for example, a number of the small gas channels instead of a single one. So this is one of the things which could be decided at the design stage. Other samples of how the gas channels could be arranged is, for example, you could think about some internal recirculation pre-designed so that a first flow enters the cell, and after that it recirculates in the outer channel and interacts with the active cathode layer. Or for the tubular cells, you can see some examples in the literature or offered by the companies where the external gas channel could be separated into the sectors inside the cross-section. So there are quite a lot of things that you could check in terms of geometrical layout. And the tricky question here is that the exact way how you're going to fabricate the cell and how you're going to, what kind of materials you're going to use will largely differ between cell of the tubular geometry, planar geometry, and from arrangement of your gas channels. So for each of them, you would have to have your own trade-off space. So overall, if you were to summarize what kind of features could be done for the gas channels, you would start even from the flow direction, because these channels could have parallel flow, counter flow, cross flows. They could have different cross-sectional shapes, or the channel itself could have a different profile. For example, there are profiles with the elbows or zigzag channels. And as I mentioned, there can be a different number of channels in the cell, in the internal layers, or for the external channel. So sometimes it could be a question whether using one single large channel of the steam or multiple small channels. And related to this, when we're making a new design or improving an existing solid oxide electrolysis cell, we could use different types of models depending on the exact design purposes at this stage. So the models for electrolysis have a similar classification in the end to the models that you would use for other fluid structure interaction problems. So the models overall differ just in the basic dimensionality, from 0D to 3D models, depending on how precise you're going to describe your phenomenon. And for some types of modeling, just 0D models can be sufficient. For example, if you are modeling chemical reactions. Another dimensionality that you could consider is temporal. So either you're obtaining steady state or transient results. Other classification is coming from how precise the physics could be described for the solid oxide fuel cell or electrolysis cell. Here, the black box models would often ignore a lot of the physics of the problem. Gray box models will try to account for a part of the physics, and the white box models, they're trying to account for the maximum of the physics. And obviously, there are many options in between, so you cannot say for many models that they're exactly white box, because they might use some additional closures, some correlations, which are coming from the experimental data. And in this classification, these models are a lot alike with the fluid mechanics. So here, the gray box models will often use, for example, some part from the neural networks when they mention the inputs and outputs, but they also account for some physics, like Navier-Stokes equation or some reduced order model which already exists. Also, how you consider your cell, it will also depend on the current goals in your design process, at which stage you are. If you are considering several levels, how you consider the process, it is called hierarchical modeling. So overall, you could distinguish between the microscale models, where one of the very precise methods is molecular dynamics, mesoscale models, models at the cell level, at stack level, they're often alike, and models at the system level, such as model-based systems engineering. And here you could see there's a wide variety of the multi-physics models which are applicable for the cell and stack levels. And for the multi-physics simulation, you would often go for a combination of some mechanical model of some thermal balance, and the fluid dynamics, transport of species, and the electrochemistry. And when we're running a multi-physics model, there are a wide variety of them. So some models can be integrated as a monolithic model with the same exactly spatial or temporal resolution. Also, you could have models which are one-way coupled or two-way coupled, where you have a feedback from your submodel. Or if it is a complex software, sometimes you could have several types of couplings in between submodels when there is different resolution in time and space, which is provided by different submodels. So those are different ways how you could optimize your modeling. So the aim of the current project is to develop an efficient and mechanically stable cell design for solid oxide steam electrolysis, and the tubular cell layout would have a single internal gas channel. So this is selected as a basis. Also, the project considers the use of a meta-surface for at least one of the layers in order to increase the overall performance of the cell. The modeling work in this project includes the structural analysis with the finite element software, thermomechanical simulations, fluid dynamics analysis, and some further benchmarking with the published and new experimental data for this specific tubular cell. So the laboratory experiments are split between the universities, and the high temperature testing here is performed by the University of Surrey. So Ajit will cover this part. And the low temperature tests are performed at the Robert Gordon University. And when designing those experiments, as I mentioned previously, in the university environment, it's important to go for the highest safety. This defines a lot the choice of the metal support for the specific tubular cell. And in this project, we are working with the stainless 316 steel and the titanium porous tubes used as a metal support. And already based on some analytic estimates for the thin wall and thick wall structures and the safety factor of 10, we could say that our metal supporting layer is going to be at least 1 millimeter thick. And in the project, finally, we're using about 2 millimeter thick substrate metal supports. So the tubular cell here is being fabricated in the lab and can be presented for thermomechanical analysis as 6 layers of the structure, including the substrate as the inner layer, silver interconnect cathode, thin dense electrolyte in the anode layer. And also on the top we would have a silver interconnect layer. So this is a simplified cell we're going to test for the thermomechanical part. And the total thickness of the undeformed cell is about 2.5 millimeters. And the materials used here, they include titanium, silver, nickel oxide, GDC, YSD, and LSCF. From the material properties, you may know that there is some difference, quite valuable, between the thermal expansion of silver as a material and coefficient of the thermal expansion for other materials which are used for this specific cell design, so that the maximum thermal expansion could be expected specifically in these interconnect layers. Also, the base case thermomechanical test that I'm going to show that they will assume the worst case conditions where both ends of the cell are fixed and there is no porosity in the layers. This will allow to obtain the maximum thermal expansion. So this is a really worst case scenario. It is coming from the density which will be considered at its maximum, basically. So we're going to I'm going to show the simulations for the 800 degrees Celsius thermal load and 1 megapascal of the internal channel of the fluid. So this is a high temperature internal steam channel. So for this thermomechanical analysis, the materials from the previous slide, they are mixed in a different proportion in order to obtain the final properties that we're going to incorporate into the model for the cathode, anode, and electrolyte. And this comes from the mass and the volume proportions that we're using for the final properties of the layers. So materials and thicknesses that we are using for the simulation, they will differ slightly from what is in the laboratory conditions. So Ajit will speak more about how the cell is in reality. And in here on this video, you can see one of the results. This is for the, I'll change the pointer. Yeah, so this is in these idealized conditions that I mentioned, when we put it into the finite element software in the steady state simulation, they can give you this idea for the worst case scenario. And this is how it looks like for the axisymmetric modeling for the solid oxide tubular cell. This results show the total deformation. So you could see that the maximum deformation is within 140 micrometers. But again, this is a really worst case scenario for these specific materials. At the same time, the wall thickness, I will reiterate, is about 2.5 millimeters. Right. So if we project the total deformation result on the undeformed geometry, we will see something similar to these counterplots. So we could see here clearly the effect of the fixed boundary conditions for the temperature of 800 degrees. And the result you see here is for this outer silver layer, which would experience one of the highest thermal expansions. So this is another view of on this total deformation. So you can see that around one of the ends, you would have at least higher deformation, areas with the highest deformation for the top outer silver layer. Okay, these are few more videos for the total deformation for the 6-layer cell, when you can clearly see the effect of these boundary conditions with the fixed conditions. So you can see the deformation for both outer surface and some deformation to the internal fluid channel. So these are just different views on our axisymmetric model. So the next slide, just a second, sorry. Oh, wow, okay, I will try to reshare the slides just now, sorry. Yeah, we're there. Okay, I hope you are able to see the slide again. I think video is a bit heavy. Okay, so the total deformation results in this slide, they're now presented for 3 cross sections in the middle. It's located evenly spaced at if we have a tube which is 100 millimeter long, these samples are taken from the 25, 50, and 75 millimeter mark. So it's counted from one of the fixed boundaries, and they show a very similar increase in the total deformation value with the radial coordinate, where 3 is radius of the internal gas channel. So this internal radius is 3 millimeters here. So this is what total deformation which comes through the wall. So this is a lot a result of the internal pressure of the 1 megapascal together with the thermal expansion. And in these figures for total deformation, you can already see the exact border where our expanding substrate, which is 2.15 millimeters, it ends, because deformation and the stress scenarios that I'm going to show on the next slide, they're going significantly to change. And in the functional layers, they have slightly higher, or for silver, significantly higher thermal expansion coefficients, you would have a relatively high deformation. So I will be showing results. On the left, it will be the full view through the wall, and on the right, it will be the enlarged areas. So here you can see almost clearly borders in between the layers. This is just another view on this thermal expansion process. Yeah, here we go. So the radial hoop and longitudinal stresses, they defined using the cylindrical coordinate system, which is placed in one of the fixed ends. And if we're talking about the middle cross section, which is at the 50 millimeters mark, for the 100 millimeter pipe, you could also see an exact border for the substrate layer, after which in the functional layers, and we plug into the model only the frictionless behavior in between those layers. So you can see that these stresses, they start fluctuating largely, and this amplitude of fluctuations is sometimes an order of magnitude higher than the stresses which are exhibited anywhere inside the substrate. So this is a combination of the different material thickness and the frictionless contacts that we incorporate into the model. So if we compare three cross sections, you can see that in terms of the substrate, when we're coming through the titanium substrate, there is not much of a difference between these three cross sections, but there are significant differences already in radial and hoop stresses in between the layers, starting with the first silver interconnect between the substrate and the cathode. So you can see this enlarged part here on the right for both stresses. And if we're looking at the longitudinal stresses only and at the strains, here the borders in between the layers become even more evident. So this is a silver layer, then you've got cathode layer, especially if you're looking at the longitudinal stress. This is the stress in the electrolyte, after the stress in the anode layer, and finished with the layer of interconnect. So by this record, in terms of radial coordinate coming through all the layers, you can see how layers behave differently. And this is a story similar to the shear stresses for different planes in the same coordinate system. You can also see the border with the substrate, and the only thing you could derive from shear stresses is basically that there is a large difference of behavior between substrate and silver and functional layers and further silver. So in these videos, you can see the difference between how the total deformation develops for the 600 degrees Celsius. This is on the top. And for the 800 degrees Celsius, this is what you have already seen. So the difference between expansion at 600 degrees and 800 degrees is about 1.5 times. This is the maximum total deformation observed in the model. So respectively, in here, it's located near the fixed connections. For the 800 degrees and for 600 degrees, it's also located in this area, but the value of the maximum deformation is significantly different. So if we take a view from the fixed connection surface, you will see how this expansion grows. And in this specific video, we allow the outer functional layers to expand, so you can see this difference in expansion. Yeah, so from this analysis without porosity and with only frictionless context, you may be able already to see the difference in this expansion. So if we fix the substrate and leave these layers to expand, you basically can see clearly how the silver expands with interconnects, expansion in the cathode, in the anode, and the smallest expansion in electrolyte. And related to this, you can see if you take a cross section and you try to visualize how these layers grow, you can already see the potential for delamination when the layers become at some difference at some distance from each other and at the microscale. So it lays the foundation for development a lot of the degradation effects, delamination, or some lack of performance, because what happens at this microscale, it significantly affects how the cell is going to perform overall. So, and around this topic for the challenges for degradation, I'm going to hand it over to Ajit. Thank you.
Yeah, am I audible? Yeah, thank you, Victoria. So very good morning to everyone. So let me share my screen. Yeah. Yeah, is okay? Yeah. Okay. So very good morning to all again. the next 30 minutes, I'll be talking about the fabrication and performance of tubular solid oxide electrolyzers. What are the opportunities and challenges? Mostly, I'll be discussing and adding my thoughts, our project results, a bit about the current work to the previous speaker, Victoria. So, yeah, let me. Yeah. So the outline of the talk would be in four different perspectives. First, I'll be talking about some basic aspects of the SOFC technology, why the SOCs are very important, and what are the uniqueness, and what are the device configuration again, and the state of or structure of the technology, and what are the existing challenges in the research. And I'll be talking about our project. Of course, I'll be adding some values to the work, and what are the fabrication methods, what exactly we are doing, and a few results. And of course, we will be talking about the challenges and approaches, how we are tackling the challenges. And I'll be talking about the market analysis, what are the investment and the cost optimization for developing the cells, and what the plant capacity and the technology readiness level or in terms of maturity, and who are the global leaders in the area of research. I'll also touch about some the technological barriers or challenges existing, and I'll also be talking about the opportunities, the place where one can look forward, or they can think about networking their own interest in the research. And finally, I'll be concluding my talk. So as we all know about or very familiar with the green energy transition at this moment, so you could realize the impact of the CO2 emission from various sectors. So if you look at the graph or the chart, the major contributors of the CO2 is mainly from the industry and the transport. So it is a serious concern in the environment. It is affecting the climate change. That's where the green hydrogen production is coming to picture, because hydrogen is a very efficient and a very promising and clean fuel, or it is contributing to the many of the industries, the products what we are daily using. So it's a potential green energy source. So producing hydrogen from the clean resource is always challenging. So it going to be one of the major research in the decarbonization strategy around the world. So that's where the SOEC is very interesting. Why the solid oxide fuel cell, solid oxide electrolyzers are very important. When you look about the performance, as Victoria discussed previously. So if you look at the efficiency, it's a one major point. It is more important. So if you look at the efficiency from the top to bottom, so the efficiency number is quite high in terms of the lower energy consumption or the electrical energy consumption, because it's need a relatively lower electron input to split the water, I mean H2O2 into hydrogen, with compared to the commercialized techniques like alkaline fuel cells, alkaline electrolysis, and the proton exchange membrane electrolysis. So it require nearly 1 point or less than 1 volt to split the water. So but whereas the well developed technique alkaline and PEM, it require more electrical input to split the water. Of course, it has also a lot of problem with the catalyst and fabrication. There are their own advantage and disadvantage in this. So in the other parameters, if you look at about the solid oxide fuel cells, I mean electrolysis with the other techniques. So the steam reforming, of course, it's a well-established technique, and the TRL level is quite high, but still you can see the impact or the problem. So it still emits the CO2 nearly 5 to 10 kg if you are continuously operating. So that's why the three techniques are very promising. The alkaline and PEM and SOCs are very promising approaches to produce hydrogen. So SOC stands in the balance, like if you could address some of the challenges, we can beat the alkaline or PEM electrolysis techniques. So the main point is the higher thermodynamic efficiency is a major advantage why we talk more about SOC, and the voltage efficiency in terms of higher heating value, because it operates at high temperature. It utilize both electrical energy and thermal energy to split the hydrogen from water. That's why the overall efficiency is always high or superior to the other two techniques. And the system efficiency, of course, system I mean in the stacks or the multiple systems together. So it is about nearly more than 90% is none of other commercialized techniques been reported more than 80% of the efficiency values. So let us now discuss a little more about the mechanism, or I'll not be more deep into the mechanism, but of course, I'd like to add some points to the Victoria, what she discussed. And before going to SOEC operation, so let us understand SOFC, the fuel cell operation. The major components are the electrodes and electrolytes. So we say the anodic part, if you are referring to the SOFC, and the cathode is, of course, in the negative electrode. If you supply any hydrogen into the anodic compartment, all the hydrogens getting oxidized and it releases an electron. So these electrical energy is a conversion of the chemical energy into electrical energy. These electrons can be utilized if you connect the load in the external circuit, and the same electrons, reaching to the another compartment in the cathode, so where it reacts with the pure oxygen. So we need to supply two gases in the two different compartments, respectively the anode and cathode. Now the oxygen gets reduced, and it produces oxide species, and it travels through the dense electrolyte membrane. It is called electrolyte. It is the role of the electrolyte just to conduct the oxygen species from the cathode to anode. And once the oxide and H plus, the oxide species combined in the interface of the anode, it produces water. So it's a harmless product. This is how the SOFC is working. And the mechanism of SOEC is just opposite. So we are converting hydrogen into water. Here we are splitting the same water into hydrogen. So that's why the cathode becomes a main component, where the hydrogen is getting produced from water. If you supply or allow the electrons back to the cathodic side, the water can split into hydrogen. So the oxide again, oxide species can travel through the electrolyte and reaches to the anode. It get oxidized into oxygen. So this is how the two species can effectively split into hydrogen and oxygen if you operate the SOAC mode. So the main beauty or the interesting factor about the technology is the one device can operate both. So you can operate in a two different modes. If you are operating under fuel cells, you will be able to generate the clean electricity from hydrogen. If you reverse the process, so you will be getting the hydrogen from the water. So if you could see, the current density is the main parameter. So when you operate the cell voltage under some, like maybe 1.5 volts, so you will be able to generate the current from 0.8 ampere per centimeter square. And if you are switching back to the electrolysis, so you will be able to generate hydrogen at the higher current densities, about 1 or 1.5 ampere per centimeter square. So what else we will be getting when compared to other commercialized techniques, like the reversible operation is a very important advantage. And of course, the integration is another added value, so that you can combine this technique with the various industry, and the hydrogen can be utilized to produce more significant product like methanol, ammonia, and the polymers, and there are a lot. So this is how the power to gas techniques is very advantage to produce valuable chemical substances. Of course, it does not have any precious metals involved, but if you look at the PEM, so they use precious catalyst. So is that's where the no the challenges are coming. But this is an effective method to produce hydrogen, and you can also produce electricity from the same device. And if you look at the configurations, so we have majorly, so we have 4 different types of the cell. So why it is important? Because the types or no, the performance or mainly depends on how you're configuring the cell. So it is generally say electrolyte supported cell. So where you can see a dense electrolyte, you can have the 2 electrodes on the either side. So anode and cathode will be fabricated on the top and bottom. And this is the cathode supported. You can have the cathode first in the bottom, and you can build the layers on the top. And the same way anode can be supported in the bottom, and the same thing can be built on the top. And finally the metal supported, you should have an additional mechanical support as a porous metallic layer or metallic substance on the top. I'm sorry, in the bottom. You can develop all the corresponding layers on the top. So you can have the cathode on the metal layer, and you can have the dense electrolyte and the anode onto the top. So if you look at the different generation is the metal supported, because the metal supported cells are very promising in terms of performance and durability and the mechanical stability. Everything it's fantastic. So if you look at the generation, so the metal support with the various layers, especially with the electron blocking layer and the cathode with the different porosity, you can see the same nickel YZ, nickel GDC in a different layer thickness will enhance the performance. If you simply see the reference, it can be or it would be a 10 times more than the basic model. So the metal supported with the multiple layers with the electron blocking configuration is a superior design to produce efficient hydrogen from water. So the same thing can be again we can define in a 2 different geometries. One can be in a planar and another can be a tubular form. So you can have a flat surface like a planar design, and the same thing can be in a tubular design as well. So where the tube in the middle portion, so we can supply the steam, or in the water can be in the form of steam, can be supplied into the middle portion where we have a cathodic material, and we have electrolyte on the top, and finally the anode. So this is how the system look likes. And so the challenge or the another compound is current collectors. So because as I told you, so we need to supply a small voltage to split the water, so we need a current collecting material to supply the electricity into the electrode circuit, especially the cathode. So we need not to think about much which material will be promising. Of course there are many reporters were saying among the various metals, the silver is a one of the most or well used material for are acting as a best current collector for SOFC and SOEC application. So you can see the number of publication and the performance, and the way we are designing the current collector onto the electrode, it also matters for the performance. So either it's a one way or two way, or the way of configuration is very important. If you look at the current density J, so it is also depending on the way you are fabricating the current collectors in the device. So it is a quite challenging no topic. So the developing the efficient current collectors in the cell is always challenging. So now we have, of course, many research people. I mean, they are working on developing the current collectors. We are one among them. So we are working on these materials. So we selected the top material like nickel YEC and nickel Syria based composite as a cathode, because it's been reported high performance cathodic material for water electrolysis. And the electrolysis we chose the YEC based, of course, is a cost effective, and we are applying this as an electron blocking layer. And we are mainly developing the cerium based electrolysis strong ionic conducting material. And the anodes, most of the layered perovskites are no best oxygen oxidizing material, so you can easily transform the oxide species into pure oxygen. So these are the materials we are working. And in terms of the fabrication, so this is how we design. So we come up with the no, the deposition method is electrodeposited silver. So we are fabricating the silver as a current collector by electrodeposition onto the electrode, and sorry, the metal support, and the functional layers, all the ceramic layers, the cathodes, electrolytes, and anodes are fabricating by the cost-effective dip coating. And of course, we gone with the thermal spray in the optimum thickness. So this is how our overall approach. for the fabrication. So the schematic way, if you look at the device, so it looks like this. So we have a porous metallic support as a tube. So the tube substrate, the dimension is about 2 mm thick and 100 millimeter long, with a porosity of nearly 40% of porosity for penetrating the gas or the steam into the electrode surface. We have a fine current collector, the silver coating onto the top. So this particular layer being fabricated by the electrode deposition. And we have another interlayer by dip coating. It's a combination of nickel oxide and silver. And the main material, the cathode layer, is a nickel oxide GDC with a thickness about nearly 50 or 80 micron thick, with the porosity of 40% by air plasma technique. And we also having a dense electrolyte layer and blocking layer. This is a bilayer electrolyte combination. Both can achieve by a dip coating. And finally, we have an anode layer as a GDC and LSCF combination. The thickness is about 50 micron thickness. So we are about, no, it's a closing stage of the structure. And finally, we have one more connecting layer to supply the electrons, and as again as a silver mesh in the form of silver wire we are wrapping onto the top. And the metasurface is playing a vital role in the electrode surface, either by the dip coating or air plasma techniques. So we're having a modified microstructure on the cathode, so where it converts the most of the steam vapors into hydrogen in efficient manner. And so you can see the real images of the silver deposition. So this is how the tube is wrapped in the counter electrode, and maybe I'm wondering if it could play. Oh, it's not playing. Okay, so this is how the silver being deposited, and you could see the cathode layer onto this top. We have a fine silver coating onto the surface. In addition to that, we have a nickel oxide GDC as a cathode and the electrolyte bilayer. Of course, it's a piece of no pictures during the experiments. And so after that, once the complete cell fabricated, we will be characterizing it a different techniques. The structures will be identified by X-ray diffraction and Raman spectroscopy, and the microstructures will be studied by scanning electron microscope. So we'll be evaluating the cross-sectional images, how thick it is, how porous it is, and all the microstructural studies will be studied. And the most importantly, the electrochemical performance will be analyzed by the electrochemical impedance analysis, and the IV will be characterized to get the current density values. And of course, the potentiometry, it's mainly applied to study the degradation effect. So how stable the cell, how long we will be able to operate without any issues or losing the voltage values. So this is how the electrochemical setup we have. So we have a metering pump. This pump can no supply the water into the control evaporator mixture. So here we have a two mass flow meters. So the steam will be, I mean, the water will be going through the mixture. This will preheat the water into 120 or nearly 100 degrees centigrade. So we will be producing the steam before entering into the tube. So we also have the carrier gas as an organ. So these organ and steam will be mixed together in a fixed flow rate. Like we'll be supplying nearly 30 to 50 ml per minute. So this will be the nominal no supply rate, and with the operating pressure up to 1 to 3 or 5 bars if required. And the mixture will be supplied again to the cell, actual cell. Here, this is where the reaction take place. The steam will be converted into hydrogen. We will be collecting back in the gas bubbler. It will condense back because it has also have some unreacted steam, and the steam, I mean hydrogen, will be collected in a gas range setup. So where you can quantitatively say that how much volume we are producing, how much we supply the steam. You can convert the efficiency as well. So this is how the performance is being evaluated, and mostly the material. So the performance is in a two different perspective. Like materials, we will be characterizing or looking into the conductivities. We are always aiming for high conductive materials. For the electrolyte, we should have a pure oxide conductivity, and the microstructure we are very interested because it will be characterized accordingly. And we will also concern about the thermoelectrochemical stability. It should have a less diffusivity for the degradation, and all the cell will be characterized. The complete device will be characterized by measuring the open circuit voltage, and the cell voltage will be derived from the open circuit values. And of course, the current density is the main parameter which tells about the performance, and mostly SOEC. So if you could achieve more than 1 or 2 ampere per centimeter squared, it's a superior value. And we'll also be evaluating the polarization resistance. It's a important parameter for operating the cell in the lower polarization resistance. Of course, the durability will be measuring the rate of degradation, nearly less than a 1 volume per stage per hour. So it should be a nominal value. So hopefully we will be getting lower degradation rate for our cells. And yeah, so this is the pictures it really look like. So the cross-sectional optical images of the tube, you could see that the fine silver coating onto the top. So this is the stainless steel with the AG, and there is a uniform coating around the tube. So the average thickness before sintering, it's close to 200 micron, and for the titanium it's about 180 micron thickness. And once you sinter it, of course, in a inert atmosphere, it will come down to closely 100 or 150 micron. So additionally, we have a deep coated cathodic material nickel oxide GDC. You can see onto the top, and you could physically differentiate the nickel oxide and GDC particles onto the surface. So it's a kind of half cell at this moment. And if you see the scanning electron microscopic images, so you could see the porous metallic substrate. We have silver coating onto the top. It is a kind of a layer somewhere. It is getting no deposited or filling the porous structure. It kind of infiltrated network. So we have ultimately we are incorporating the silver into the metallic substrate to improve the electronic conductivity, because we are supplying the electrons through the current collectors. So we can confirm this coating by X-ray elemental analysis. So the point mapping confirms that the one is a substrate here. It shows a typical stainless steel material, and these two particles or belongs to the silver. So the peak above the silver can be clearly shown. It confirms the coating of the silver in the stainless steel substrates. And the beautiful backscattered electron image shows the different combination and how the current collector and the nickel oxide GDC cathode material is distributed. You could clearly identify the presence of the material by mapping, and you could see that nickel oxide and GDC, or this is YSE, so that you can see the zirconium peaks in the distribution. And of course, we also found some silver, because the silver is a fine layer. It's about less than 50 micron. It is throughout the surface mixed together with the nickel oxide and YSE. And so what are the challenges? So we are having, of course, the efficient current collectors are a bit challenging. So we are working out on this, and making a uniform layer of the nickel oxide with the infiltrated structure is quite challenging. And so what are the other challenges with respect to the materials? That the degradation, we critically looking into reduce the degradation effect, because the cell it's operate under high temperature. It undergoes a lot of thermal stress, and there could be a lot of interdiffusion of elements between the layers. And if we are interested in the reversible operation, it also affect the or increase the degradation rate. Of course, the operating parameters, because we are changing the voltage, and the different partial pressure will also affect the cell performance. So we are looking into to addressing the degradation issue, because this particular no problem is so challenging for commercializing the cell. All the maybe the rest of the things are mostly optimized by many of the researchers. So we will be seriously looking at this problem. So we will be doing the electrochemical impedance. If you look at the long-term operation, like 2000 to 20,000, you could see the increasing the impedance arc, so that the overall resistance is getting no higher because of the delamination of the material from the surface. You could see the real images. This particular images is Sunfire, Germany. So they are working on the planar cells. So they are keep on reporting the delamination or degradation of electrode surface, and the SCM images also confirms that you can clearly see the delamination, or the kind of crack, or I would say from the electrodes and the metallic layer. So these are the critical issue, and of course we will be monitoring the no cell voltage versus time, and it should maintain the constant electrical output for the long time operation. So at a different current densities, it should give a stable current density values for the if you're operating more than 500 or 600 hours, because below the hours it should be fine. And so what is the real causes, or what makes the cell get degraded? It is again, as I told you, our Victoria also explained. So it's a kind of interdiffusion effects and the particle agglomeration, and of course a lot of corrosion issues. So our technique, like the silver coatings, will address the corrosion effect, because silver has less corrosive and is a noble metal, so it can effectively increase the current collection, so we can tackle this corrosion effect. And this is how the previous report says that once so it has a degradation, you will lose the contact points between the nickel oxide GDC and the current collector, so it has a serious issue. And so the interdiffusion again is a important issue, so we need to be very careful about the interdiffusivity between the anode and the electrolyte, because the strontium species are tend to react with the LSCF. It produce the insulating strontium zirconate phase. It is absolutely no resisting layer, so it will lower the performance. So the combination of all these stuffs will stop or resisting the commercialization of the particular technique. And overall, so our project, so we have a goals to mainly, so it's a major points here I have to given, like we are trying to improve the efficiency. So our plans are to produce the cells in the metal supported tubular configuration with the meta surface, so it ultimately helps to improve the efficiency, and it address the most of the mechanical challenges, and it gives a overall increase in the output. Of course, the metal configuration, I mean the tubular configuration, also help us to for the easy stacking for the integration. It is a major advantage. And of course, we are working on the tackling the corrosion issue, the silver deposited current collectors. So it is a important approach or the plan to address the corrosion effect, and what we are expecting from the approach. So to produce or fabricate the efficient current collecting layer or interconnection onto the cathode surface. And we are working on the cost. Of course, um, adopting the cheapest technique like dip coating. Of course, spray, I would not say it is a cheap, but still in terms of the performance, the spray coating method, it's very efficient to have a very fine coating onto the ceramic layers. And we are also know the way we select the materials to reduce the cost, because the stainless steel is the cheapest material, and the zirconium electron blocking layers, YSE based material, the incorporation will also reduce the overall cost of the cell. And of course, it meets the no economical fabrication, so we will be able to easily stack with the cheaper manner, so we believe. And the third aspect will be the market analysis, and here we could see the how much investment is required to develop these techniques. So the report says like nearly 1,000 plus dollars or pounds are required to develop for the single cells, if you are aiming for the current density is close to 1. So it's a huge value, I would say. So that's why the cost is a very important parameter. One, if someone is thinking about to commercialize this, it's not much affordable, I would say. So this is the specification, and again the optimization, the cost optimization. If you look at the graph, over the years, so the production is getting higher. So people are, I mean, the industries are coming forward to develop more cells. It's close to more than 1,000 cells they are producing in the cost of $100 for the kilowatt capacity. And I would say this number is a nominal, like it's not a fixed one. You cannot no immediately get the cells with 100 pounds. It's not true, because it depends on the configuration, what power density you are looking for, what the size, and it depends on a lot of factors. So generally it is an optimal value that you could get or invest about 100 plus pounds. You will be able to generate or get the cells for producing the hydrogen. So this is a real cell. I would just for showing you how it look like the stack case, like it has a more than, I mean, nearly 150 cells with a size of 4 into 45 centimeters. And perhaps the SOEC is not fully optimized, I mean, commercialized. There is a no megawatt scale successfully operating in more than 5 or 6 years. Especially in UK, there is a no current system is available. It's a fact. And if you look at the factory estimation, so if there are many industrial companies, they are working, I mean, developing these systems as a stack. So from their report, so they say it's like, what is the distribution of the cost? So the material cost more, like nearly 58% of it occupies the overall cost, about 800 pound or dollars for the stack. And the others, like fabrication techniques, I mean, the characterizing, it's also consume a lot of money. And building a stack, like, it is always challenging, and it's not affordable, of course, at this particular time. And the cost per the stack systems, if you are planning to, because 1 ampere per centimeter square is a decent performance, I would say. You can plan about like 25 pounds. It's a reasonable value you can invest. You can build a system for the stacking. And the capacity, what is the real case or the real picture you could see from the plant. So there are many important, I mean, the famous companies, they are building large capacity plants, like the capacity about 600 plus normal metric cube per hours of hydrogen can be produced. And these many hydrogen demonstration plants being built by the many companies, and mostly German companies and Netherlands and some of the European companies are investing, and they are commissioning the performance in more than 20 years, and it is operating successfully. And so the level of the technology readiness level is about, the for SOEC it's about 5. It's not very the beginning stage. It's not fully commercialized. If you look at the performance, I would say it is a no. If you address the degradation effects and challenges, we can fully commercialize near to the PEM and alkalines, because if you see the PEM and alkalines all almost commercialized. And again, adding to the point to the previous slide, so where it exactly stands, so it is in a medium term maturity, about 5 to 10 years of time. So the SOFC can be fully commercialized if provided, like, a lot of research efforts need to be done. And the efficiency is again a highlight. So if you look at PM and alkaline is a competitor for SOEC, and but if you address the problem, so it can beat or near or close to the technology. And other techniques are, no, though it is taking more time, it is less efficient, like 1.5 or nearly less than a 1% of efficient techniques. So this is where the SOFC stands in terms of maturity or commercialization. And here, who are the global leaders? They are very successful in developing huge systems in the stacks. And the Sunfire is it's a well-known, or the top people, I would say. They are producing the stack more than 500 cells together in a kilowatt, or maybe some devices or the gigawatt capacity, and it's being operational. So now they are this particular system, it started in I think 2019. It's more than 3 years. It's been operating very successfully, and there are other companies, Fuel Cell Energy, Ceres Power UK, and Bloom Energy, and there are of course a lot of companies. There are the top in the world. And so still these techniques face a lot of technological barrier. Is the one is cost, because there is a no fixed no menu for getting a cell in a effective cost effective way. So it is always questionable, so what cost we can afford it. So it is, the cost is always challenging, and the long time operation is again challenging, and demonstration of the cells for the long time. I'm talking about more than 1,000 or 2,000 hours, if because we are spending huge money for the stacks, so the performance should be long. So that kind of challenges we have in this technology. And the multi-stacking, it's quite challenging. Of course, assembling the cells with a proper stacking, it is always challenging. And the commercialization, it's related to the previous one. Of course, integrating the system is maybe a quite easy, but still it involves a lot of efforts. And the fourth aspects will be the future perspective, or like so how the technology will transfer. So you can think about the co-electrolysis. So it's not only this system is producing hydrogen from water. You can also convert the CO2 into carbon monoxide. This monoxide is mainly a important precursor for producing most of the industry, like pharmaceuticals, and no, a lot of organic stuffs can be produced from the carbon monoxide. So these system can play a multiple using a clean hydrogen, clean electricity, and producing the carbon monoxide from dioxide. So these again, you can integrate in that aspect, and the single device can be operated in a fuel cell operation and electrolysis. This is the future aspect of all the opportunities where you can look into. And of course, if you could integrate, because the system is operated in a extremely high temperature, we need not to spend more money, or you can cut down the cost if if you have a no external heating, or utilizing the waste heat from other resources like nuclear energy or the high thermal reactor. Maybe 200 to 300 degree is excessively spent, so that thermal energy can be utilized to operate the system more efficiently. We could increase our furnace, or the heating inbuilt heating element can be heat up to maybe 200 500 degrees Celsius, I would say. So these are the opportunities for integrating the system with multiple other systems. You can build a sustainable chain value for producing a very good or important organic substances and clean energy resources. And our targets are like, we are looking into no perform I mean increasing the performance with a lower degradation rate, and we are trying to build the system with a lower cost and durability, and the scalable system for the integration. And what we are exactly looking for stacking design. So we are working on the new designs for the stacking, and we are looking for some industrial partnership for commercialization, of course. And so this is all about the bridging the gap between the ideas and the real demonstration. So enhancing the performance is always challenging, but we almost we working on to that level. And so hopefully we will be developing the next generation metal supported solid oxide cell, which can be play a huge role in the green energy sector. And with this, I conclude with a summary. Like SOC, like solid electrolysis, is a promising technology which can offer green hydrogen with a very high efficient manner. And we are working on the fabrication part and testing the tubular cells. And this Metasys project is addressing the most critical challenges in the technology to solve the we are developing through the microstructure, like the modified meta surface will give you the best result, or the conversion of the steam to the hydrogen. And we also adapted the cost effective fabrication, which also helped to reduce the cost as well. And the project is also studying the microstructural effects, the metastructure, the effect of the surface effects, and the effects of various layers, especially in the interfaces, as Victoria presented. So how it expand, or the thermal expansions during the operation. So through the modeling will help to understand or to build the better system in the future. And our conclusive understanding both from the experimental, because I'm working on experimental for the fabrication and testing the devices, and her inputs, like they are working on the modeling, especially the collective no informations is very helpful to develop the stacks for the future commercialization. Okay, so I thank our collaborators and mainly my investigators, Dr. Chong and Dr. Barman, and I thank Professor Faisal, Professor Mamdoot, and Anil for their valuable inputs. And I also thank Victoria for joining with me today, and I also thank Vinod for his help for this project. Thank you very much. I'd be happy to take some questions if you.
Thanks,
Amazing.
Victoria.
Thank
Yeah,
you very
thank
much for the presentation. I have unmuted people that would like to ask questions. So if you'd like to go ahead and ask a question. Vineeth, if you'd like to go first.
Yeah. Thanks, Victoria. Thanks, Ajit. I have a very small question to Ajit. Ajit, you showed me some of the planar plates. You measured the electrochemical impedance spectroscopy. So do you know the temperature of the experiment?
No, this impedance.
Yeah.
So you can compare a particular temperature. Like if you are operating the cell at 600 degrees centigrade, you can measure the impedance, and you can operate the same device at the same temperature for the long time. Say for example, so we are starting the cell at 11 a.m. and you are measuring the impedance at 11 a.m. at 600 degree, and the same impedance can be recorded in the evening 5 p.m. at the
Mm.
same temperature. You can measure the impedance the same level. You could see if the cell is getting degraded, you could see the increase in the overall resistance. So the impedance arc will be expanded so that you can understand how much the cell got degraded. So this is how things works. You can plot the impedance with respect to time, not with respect to the temperature. You have to maintain the constant temperature for recording all the data.
Okay. Okay. Yeah, makes sense. Thanks. Yeah.
Thank you. Yeah.
Ahmad, would you like to go next?
Yes, can you hear me? Yeah.
Yeah, all good.
Right. So my question is to Ajit. Quick questions in terms of the voltage in one of your slides. I don't know whether you can open again your slide and show the voltages level that you used.
This one. Okay, sorry. So may I know which slide you're interested? This one.
The voltage level that you use. Not this one. I think previous one. For the back, I believe.
Yeah, no problem.
Yeah, this one. Yeah.
This one.
No, the next one. Sorry.
Okay.
The next. Yeah, this one.
Oh, okay. This is
Yeah,
for
just
current
yeah.
collectors. Yes, yes, yes. Yeah, yeah.
Yeah. So for that bottom left slide, I mean the figure, the voltage seems to be decreasing from 1 volt to say 0.6 volt.
Yeah.
Is that sorry? I missed some of your presentation, so I'm trying to understand. What causes it to reduce, or that's when you set it up to reduce? That's the first
No.
question.
So this particular data, what exactly it tells. So the voltage, mainly I understand it's from SOFC. Okay. So the voltage is it's reaching it 1 volt. It's a electricity produced in the device. When you start generating the current from the device, the voltage will drop, the current will increase. So you could see here, so it is starting at a constant voltage. So all the three, it's a different current collecting configurations. So if you look at the third case, this one is third, I believe. So it start with the 1 volt, when you start the IV, so it's supposed to be drop because you are withdrawing the electrons from the device. You are
Okay.
producing electricity from the device. It's supposed to decrease. It is in a common behavior that in the IV. So the initial potential will be dropping when you are withdrawing the current. So the current should increase in the milliampere, like it is a 0.35 ampere you're producing, automatically the current, I mean voltage will drop. So it is a normal behavior, I believe, from the current and voltage phenomena.
All right. The second question, which is on the flip side of coin. So I believe that is scalable.
Uh, so you're talking about the SVC? Yeah, of course. It's scalable. Yeah.
So suppose if you start with, say, 10 volts, for example, or 5 volts, which is within the electronics design, is 5 volts to start with. So that does that going to give the same effect of the voltage decreasing?
Yeah, the decrease of the voltage is no common behavior for all the devices, irrespective of the voltage you operate.
Okay.
So
Okay.
so the maximum voltage, it depends on the area of the electrodes. If we are working on like a 5 cross 5 centimeter inverse of the total surface area of the electrodes, you can expect up to 3 volt is a maximum from the OCV I am talking about. It's an open circuit will be a no highest value, and if you are no reducing, I mean subtracting the impedance values, the polarization resistance from the OCV, you will be able to calculate. Maybe I can show you the next slide. Yeah, these. So yeah, from the OCV, you will be able to calculate the cell voltage. It should be like 0.5 to 1.5. It depends on the area for the cell or the size of this device. So it can go more than this for SOFC, I would say. But for SOEC, it should be a very lower voltage input for, like, I would say less than 1.5 volt should be sufficient, because water splitting voltage is close to 1.2 volt. So you will be efficiently split the water. Yeah, but automatically the open circuit voltage or the cell voltage will decrease when you withdraw the current. So let me make it more clear when I show the device operation mechanisms. Yeah, so here, so we are what exactly it's happening, like all the steam is converted into hydrogen by receiving the electron input from the potentiostat, and the oxide species is traveling through the electrolyte, and here it getting oxidized by releasing electron. That's why we are getting the current. So the anodic surface, all the oxide species getting oxygen molecules by oxidation. So it releasing an additional electrons. So more you produce an electron, it is an indication that you are converting most of the steam into the into hydrogen. So the applied voltage is respect to split the water. Nevertheless, you are getting more current, more the moment you are converting most of the steam into hydrogen. So most of the oxide species will convert into oxygen.
Okay, so
So
can I also assume that the higher the voltage, the quicker the current draws?
yeah, so yeah, that's why. So this particular graph, what you see here is for SOFC, I would say, because it's a nominal behavior that because it have a high voltage, because you can convert the hydrogen into electricity here. So it can supply more, it's ready to supply more electrons from the device. So that's the indication of the voltage. And if you start withdrawing the electron from the device, so your current will increase, automatically the voltage will drop.
Okay, thanks very much. You're helping me with the
Yeah,
simulation I'm trying to model.
it's a scenario where you can think about, if you fill the water in a bottle, so it's a capacity, how much water it occupies. It's all about voltage. When you
Yeah.
release, the moment you release a tap, it is no automatically the capacity of electrons will be start flowing through your external circuit, or you're withdrawing, or you are using the electrons from the tank of water kind of things. So automatically the level will decrease, your outflow of electrons will start. So this is how you are getting the current, and you're dropping the voltage. Yeah.
Oh, thank you very much. You've been very, very
Okay.
helpful. I'm
Yeah.
trying to figure out something on my modeling, so I think I got a picture, then I should be able to do it. Yeah,
Yeah. Okay, thank you.
that's all from me.
Well, thank you very much. Just in the interest of time, I think we'll call it a day there. This webinar has been recorded and it will be uploaded to our YouTube channel. I've just put the YouTube channel link in the chat. And if you do have any more questions, just contact anybody that's spoken today or myself or anybody at the National Subsea Centre or RGU if you need any support. So yeah, thank you very much. And look out for the next one.
Thank you.
Thank you all. Thank you.
Thanks for coming.